All right, so yesterday we were talking about satellite motion, and we said that in order for one object to orbit another, there has to be a centripetal force that is being provided by the force of gravity. Okay? Because it is gravity that makes something orbit something else. Right? And we said that that's going to set up most of the time like this. mv squared over r equals big G times mass 1 times mass 2 over r squared. Okay? One of those masses is going to cancel. Which one? The smaller one, right? The satellite's mass is the one that's going to cancel. Right? So that's what we're looking at here. Now, the other thing that we pointed out, and it's going to be important for this question, is that sometimes we might be asked to calculate or be given the period instead of the speed. If that's the case, then we're likely going to have to substitute into this formula the formula for V. Okay? We know that V equals 2 times pi times the radius over the period. Right? In a question where, for example, I'm asked to calculate radius and given period, okay, or sorry, I'm asked to calculate, yes, radius and given period, or the other way around. Anyway, but there's a combination of givens here that will result in us not being able to just plug into this formula, solve for V, and then solve for that. Okay, so we have to be able to substitute this formula in for V. All right, now in this formula, V is squared. So if I'm going to substitute this formula in for V, what do I have to do to it? Square it. Okay, what's 2 squared?
4.
Pi squared?
Pi squared.
Right, r squared, t squared. All right, so I can take that now, right, take out the V, and just move this into the formula. Right, so now I've got 4 pi squared times r squared over times m over t squared times r. Now I've got an r squared here and an r on the bottom, so that's going to go away, and I'll be left with 4 pi squared times r times m over t squared equals big G times mass 1 times mass 2 over r squared. Okay, now I can manipulate and solve for t. Okay, because that's one of the things the question's going to ask me to find. Okay, so in this question right here, it wants me to calculate the orbital speed and the orbital period. So using what I just did here, I'm going to solve for orbital period first. Okay, once I have that, then I'm going to go back and solve for orbital speed. Okay, so I want to get t by itself using this formula. Right now, t's on the bottom. If I want to solve for it, it needs to be on the top. All right, so I'm going to multiply both sides by t squared to bring it over here. Multiply both sides by r squared to bring it over to this side. What's r times r squared? R cubed. Okay. I'm going to bring the rest of this stuff over, so I've already gotten rid of t squared, gotten rid of r squared. Okay. Now I'm going to bring big G and the 2 m's over. Okay, and what's going to happen to this m and this m? They cancel, okay? Because they're the same number. All right, so that's going to solve for t squared. What do I want?
T.
So what do I have to do? Square root. Okay, so now when I plug in my numbers, okay, I'm going to have 4 pi squared times, and then they gave me the, well, actually, they gave me the ability to calculate the radius. Okay, I'm going to have to figure out what it is here. So I'm going to go in my calculator. 6.38 E6 plus 912,000 meters. All right, so there's my radius, 7,292,000. So 7.292 times 10 to the 6. Okay, and that's cubed according to my formula. Okay, and then I'm going to divide that by 6.67 times 10 to the minus 11 times the mass of what's the other mass? Earth. Yeah. Okay. So that'll be 5.98 times 10 to the 24. Okay. All right. So now if I'm doing that, I should be able to calculate how long it takes that Landsat satellite to make one complete orbit of the Earth. Right? So there's certainly a bit of manipulation here that's involved. So I'm going to have 4 pi squared, okay, times 7.292 E6 cubed. Right, then I'm going to divide that by 6.67 E negative 11 times 5.98 E 24. Okay, so it's telling me, sorry, and I have to square root that. All right, so it takes 6.19 times 10 to the 3. What are my units for this? Seconds, yeah. It takes just a little over 6,000 seconds for it to make one complete orbit of the Earth. All right, that's what, an hour and a half? Something like that. 1.72 hours. Okay, for it to orbit the Earth one time. Okay? So it's moving pretty fast. Incidentally, that's the other thing the question asks us to find is, how fast is it going? Well, now that I know T and R, can I calculate V pretty easily? Yeah, I certainly don't have to go back into this big formula to do that, okay? Nor should I. So I'm just going to go 2 times pi times 7.292 E6, okay, and divide that by the 6194. Okay, so it's moving at 7.4 times 10 to the 3, 7.40 times 10 to the 3 meters per second. Okay, remember how we said that near the Earth's surface something would have to move at almost 8 kilometers per second? That's 7.4 kilometers per second. Okay, so it still has to move pretty fast.
Does the International Station, is it like when it's space still?
No, the International Space Station is in low Earth orbit. So they go around with about the same period as that. Okay? They get, I think Chris Hadfield said they get 18 sunrises and sunsets per day on the International Space Station. Right? Because they constantly are going around the Earth. Right? So the sun falls behind the Earth as they orbit, and it does that 18 times a day. Right? So it's a little over an hour per orbit. All right, everybody follow the manipulation there. Okay, just plugging in and then, moving things around. Nothing you guys can't handle. Okay, I want you guys to try these ones. Something to watch for, because this is a very common trick with satellite motion questions. Giving you the height. Okay, if it's giving you the height, what do you need to add on to that? The radius of the Earth, right? Okay, if it says height, altitude, or above the surface, it's trying to trick you. Okay? It's trying to see if you remember you need to add on the radius of the Earth in order to get the center-to-center distance that we need. All right, so give those two a try, see how we do. So, first thing we have to do, okay, since we're calculating the orbital speed of the International Space Station, is recognize that, of course, it's a satellite, and that the centripetal force is being provided by gravity. The next thing we have to do is we actually have to have the actual orbital radius, right? Which is going to mean we have to go 6.37, actually the textbook uses 6.38 times 10 to the 6 meters, okay, plus 359,200 meters, because it's in kilometers. All right, so if we do that, we'll have our actual orbital radius. So 6.38 E6 okay, plus 359,200. So there's our actual radius, 6.7392. Okay. All right, so now we've got our actual orbital radius. Now we can solve for the orbital speed by going mv squared over r equals big G times the mass of the Earth times the mass of the satellite over r squared. Okay, the mass of the satellite's going to cancel right off the bat. Now I don't have to move it around. Pretty okay with that so far? Okay. I want to get v by itself, so I'm going to multiply both sides by r. When I do that, the squared on the bottom is going to cancel, and then I need to square root this in order to get v. So I'm going to have 6.67 times 10 to the minus 11 times the mass of the Earth. Textbook uses 5.97, okay, times 10 to the 24, divided by 6.7392 times 10 to the 6. Sorry, 5.97. Okay, and then will be divided by our answer from the last one. All right, so we're looking at, I'm sorry, I have to square root that. All right, so it's moving at 7.7. No, we have 4 significant figures. Okay, so 7.687 times 10 to the 3 meters. Why do I have 4? Right, the other ones are what we call absolute values, okay? If it comes off of your formula sheet, it contains no uncertainty. Okay, it contains no uncertainty if it comes off your formula sheet, so it does not affect your significant digits. Okay, everybody clear on that one, because it comes up sometimes. All right, how many people have done number 2? All right, I'm going to give you a little bit more time. This one you're using orbital period, so you're going to have to do that thing that I showed you before. Okay, the substitution thing. That's what you have to do here. All right, I'll give you a couple minutes on that one. All right, let's have a look at this one. So we have the X-ray satellite taking pictures of the universe. Okay, it's orbiting the Earth at an altitude of 114,593 kilometers. So first off, I need to change that to meters, and then I have to add it to the Earth's radius. Okay, so I'm going to have here to start off with 6.38, because we're using the textbook numbers here. E6, okay, plus 114,593, and then putting it in meters means 3 more zeros on there. Oh, that's supposed to be a plus. All right, so there's our orbital radius. Okay, it's really, really big. This thing is really far away, so that it actually doesn't get interfered with by any radio transmissions from Earth. Okay, so we've got that orbital radius now. Now we can find the orbital period. So instead of using mv squared over r, okay, is big G times m1 times m2 over r squared, I'm going to substitute in for v, okay, in order to get the period. So that's going to mean m times 4 pi squared times r over t squared. Okay, so again, I did this. I went 2 pi r over t. I squared it all, so it was 4 pi squared r squared over t squared, and then I substituted it in here. Okay, that made the r squared cancel the r on the bottom, which is why it's no longer squared there. Okay, so I'm looking for period. I'm going to bring period over to this side here. Okay, I'm going to bring r squared over here, and then I'm going to divide both sides by big G times m1 times m2, which is going to make the mass of the satellite cancel. Okay, and then I'm going to square root that. So what I'll be left with is the square root of 4 pi squared times that 1.2 times 10 to the whatever that I have in my calculator there. Okay, all cubed. Okay, divided by 6.67 times 10 to the minus 11 times the mass of the Earth. We're using the textbook's number, so it's 5.97 times 10 to the 24. Okay, so when I'm plugging in my numbers here, okay, 4 pi squared, 4 pi squared, okay, times my answer cubed. Okay, so there's the top. Now I'm going to divide that by the bottom. 6.67 e negative 11 times 5.97 e 24. And then I'm going to square root that. All right, So that's how long in seconds it takes this X-ray satellite or X-ray telescope. That's how long it takes it to orbit the Earth. Okay, is it a lot? Yeah. Well, it's a lot further away. Okay, if we divide that by 3,600, okay, we find that it takes 116 hours for it to make one complete circuit of the Earth. So it's way out beyond the geosynchronous satellites that we talked about yesterday. Okay, it's a long, long way away. All right. Any questions on how those ones work there? Okay. All right, so I'm going to have you guys work on a few. I think I've got 6 or 7 satellite motion questions in the worksheet booklet, okay, that I'm going to have you guys work on, and then we'll see how we're doing after that. Okay, so there's two ways to calculate the orbital period of Mars. We could set Mars up as a satellite of the Sun and go FC equals FG. Okay, that's using satellite motion laws in order to calculate the period. If I do it that way, I'm going to get the period in seconds because I'm using really big numbers, right? If I use Kepler's law of periods, I can set it up like this. And we actually did this one right out of the textbook. Period of Earth squared over the radius of Earth's orbit cubed, okay, equals the period of Mars squared divided by the radius of Mars's orbit cubed, okay? Did I not put in the radius of Mars on that one?
I think it may have been in question 5.
That's where it was. It's in question 5. Right here. Radius of Mars' orbit, 2.3 times 10 to the 11 meters. You'll need that number in order to do number 6. Okay. So let's go back to this one. Now that we have that, okay, I'm going to bring radius of Mars' orbit over here. Okay. And then I'm going to square root all of this to get the period of Mars' orbit. Right. So when I do this, I'm going to have 2.3 times 10 to the 11 cubed, okay, times 1 squared, period of Earth's orbit, divided by, and here's the other thing, if I used meters for Mars' orbit, I have to use meters for Earth's orbit. I can't use one astronomical unit now. Okay, I'll get a really weird answer. Okay, so 1.50 times 10 to the 11 cubed. Okay, so essentially then, all we're doing is taking this number, dividing by this number, and then square rooting. Okay, so we'll have the square root of 2.3 e 11 cubed, okay, divided by 1.5 e 11 cubed. All right, so 1.9 years is the period of Mars' orbit, according to Kepler's law of periods. Okay. Now, is it possible that on a test you could get a question that's a satellite motion question that would be able to be solved 2 different ways? Yeah, it's possible. Okay, I might make up a question on a unit exam that says, here's some information about a planet, solve for the radius of its orbit or the period of its orbit, and if you look at it and go, hey, I've got enough information to use Kepler, by all means go ahead. Okay, Kepler's a lot quicker, uses smaller numbers, but you can also solve it using FC equals FG. Either way would work. And the other one's giving us trouble. How many people have done all 6? Okay, keep going then.
So I was wondering,